Hi everyone, welcome back to another video from my channel. In our last video we discussed about impulses and momentum, talking about the impulse momentum principle and the conservation of momentum and how we could use those concepts to be able to solve questions. Today, however, we will be learning about the statics of a particle. To begin, a particle or a rigid body is in static equilibrium if it is at rest and the resultant force acting on the particle or rigid body is zero. To solve problems in statics, we should draw a diagram showing clearly the forces acting on the particle, resolve the forces into horizontal and vertical components, or if the particle is on an inclined plane, into components parallel and perpendicular to the plane, then set the sum of the components in each direction equal to 0, and then solve the resulting equations to find the unknown force or forces. We can also use force diagrams to model objects in static equilibrium and to solve problems involving weight, tension, and pulleys. So now we will do a question from exercise 7b from the M1 book, which is number 5, that says a smooth bead B is threaded on a light inextensible string. The ends of the string are attached to two fixed points A and C on the same horizontal level. The bead is held in equilibrium by a horizontal force of magnitude 2 newtons acting parallel to CA. The sections of the string make angles of 60° and 30° with the horizontal. So for number 8, to find the tension, first we will have to draw the particle. Here we have 2 newtons. Here we have mg, where m is the mass of the bead and g is the gravitational acceleration, which is 9.8. Here we have tension acting at an angle of 60° to the horizontal because of alternating angles. If this is 60, and this should also be 60 because this is a parallel line, and similarly this also should be tension with an angle of 30 degrees using the same logic. Now we can resolve horizontally, and towards the left we can see that there should be a force of 2 newtons to the left. Similarly, due to the component of tension, which is at an angle of 60 degrees, this should be T cos 60, because as we know, if this is tension and if this is the angle theta, then the horizontal component should be T cos 60 or T cos theta, and the vertical component should be T sin theta or T sin 60. And similarly, towards the right, we also have tension, and for the horizontal component, this should be T here, and this is 30 degrees. Therefore, this should be T cos 30. So therefore, resolving horizontally, we can say that T cos 60 plus 2 newtons, which is towards the left, should be equals to T cos 30. And making T as the subject, we can write T cos 30 minus T cos 60 is equals to 2. So therefore, taking T as the common factor, we can say T whole multiplied with cos 30 minus cos 60 is going to be equals to 2. So therefore, the tension is going to be equals to 2 divided by cos 30, which is root 3 by 2, minus cos 60, which is going to be half, and this should be approximately equals to 5.46 newtons, and this is our answer. For number B, we have to find the mass of the bead. So therefore, by resolving vertically, we can say that there is weight acting downwards. Similarly, there is a component of tension which acts vertically. So this component should be T sin 60 because this is 60 degrees. And towards the right, we also have tension T. And because this is 30 degrees, therefore the vertical component should be T sin 30. So therefore, resolving vertically, we can say that t sine 60, which is upward, plus t sine 30, which is also upward, is equals to the weight, which is mg. So therefore, m is going to be equals to t sine 60 plus t sine 30 divided by 9.8, and plugging those values, we get 0.76 kgs for the mass. So for number C, we have to state how we use the modeling assumption that the bead is smooth. So in our case, we have seen that the tensions on either side of the string are equal, meaning that there must be no friction between the bead and the string. So this is how we manage to use the assumption that the bead is smooth. So therefore, the tension on either side of the string is assumed to be the same. And this is our answer. So for number 11, a particle A of mass 2 kg rests in equilibrium on a smooth inclined plane. The plane makes an angle theta with the horizontal, where tan theta is equals to 3 by 4. The particle is attached to one end of a light inextensible string which passes over a smooth pulley as shown in a diagram. The other end of the string is attached to a particle B of mass 5 kg. Particle A is also acted upon by a force of magnitude F Newton down the plane along the line of the greatest slope. For number A, we have to find the magnitude of the normal reaction force between A and the plane. So let us draw the diagram for this. So if this is A, we have a force F newtons towards the slope, and perpendicular to the slope we have the normal reaction force. Vertically downwards we have mg, which is the weight, and in this case is going to be 2g. And because we know that the angle between the slope and the horizontal is theta degrees, so therefore we can also say this is theta as explained in our previous videos. So therefore this component of weight should be mg cos theta, and this one should be mg sine theta. So therefore we can say that resolving vertically with respect to the plane, the normal reaction force is going to be equals to mg cos theta, and in this case it's going to be 2g cos theta, because we know that tan theta is equals to 3 by 4, which is opposite divided by adjacent. Therefore, using the right angle triangle, if this is theta, this should be 3 and this should be 4. Therefore, this should be 3 squared plus 4 squared, and then a square root over, which should be 5. Therefore, cos theta must be the adjacent divided by the hypotenuse, which is 4 by 5. And so the normal reaction force is going to be 2g multiplied with 4 by 5, which is approximately equals to 15.7 newtons. For number B, we have to find the value of F, and drawing the figure again, here we have F along the plane. We also have mg, or 2g in this case, acting vertically downwards, and in this direction we have the component 2g sine theta, because this angle is theta, and we also have tension acting parallel to the slope, which is connected by a pulley, which is also containing a mass B of 5 kgs. So the weight of B should be 5g, as you can see here in this line. So therefore we can say that tension is the one that is balancing the weight of B. So resolving vertically for B, we can say that tension has to be equals to 5G because it is the only force that is balancing the 5G, which is the weight of B. So therefore for A, we can also resolve parallel to the plane and say that F plus 2G sine theta is going to be the tension, which is also 5G. So therefore F is going to be T minus 2G sine theta. The tension is going to be 5G, and sine theta is going to be 3 by 5 because we know that sine theta is equals to opposite by hypotenuse. So therefore the opposite is 3 and the hypotenuse is 5, which is roughly 37.2 newtons. And this is our answer. For number C, we have to state how we use the fact that this pulley is smooth in our calculations. So therefore we can say that there is no friction between the pulley and the strings, meaning that the tension on either side of the string is going to be same. And this is our answer. For number 12, a particle of weight 20 Newton rests in equilibrium on a smooth inclined plane. It is maintained in equilibrium by the application of two external forces as shown in a diagram. One of the forces is a horizontal force of 5 newtons. The other is a force P newtons acting at an angle of 30 degrees to the plane as shown in a diagram. We have to find the magnitude of the normal reaction force between the particle and the plane. So if we draw the particle again, we have normal reaction force that is acting perpendicular to the plane. Vertically downwards, we have mg, which is 20 newtons in this case. And we also have 5 newtons acting here. And this angle should be 45 degrees because these two are parallel lines. So these are alternate angles, which should be 45. And here we also have P newtons acting, which is at an angle of 30 degrees to the plane. And this is 45 degrees. So first of all, we have to resolve parallel to the plane and say that this will have an effect of 20 sine theta because this is theta, which is 45. And similarly for the 5 Newton, we can say that the component in this direction should be 5 cos 45, and for P newtons this should be P cos 30. So therefore we can say that P cos 30 is going to be equals to 5 cos 45 plus 20 sine 45, because these two forces, the 5 cos 45 and the 20 sine theta, which are the components of the forces, are equal to the component of P in this direction, which is P cos 30. So therefore we can find P, which is gonna be 5 cos 45 plus 20 sine 45 whole divided by cos 30, which is exactly 25 root 6 by 3 newtons. And resolving perpendicular to the plane, we can say that here this is going to be R, and we also have 5 newtons acting here with an angle of 45. So this component should be 5 sine 45. And similarly in this side we also have P here with an angle of 30. So this component, the vertical component of P should be P sine 30. And vertically downwards we have 20 newtons. So therefore the vertical component of 20 newtons with respect to the slope or the line is basically 20 cos theta, which is 45 in this case. So therefore we can say that r plus p sine 30 plus 5 sine 45 is going to be equal to 20. So therefore r is going to be 20 minus p sine 30, which is 25 root 6 divided by 3 sine 30, which is half, plus 5 into sine 45, which is 5 into root 2 by 2. And the answer is roughly 0.40 Newton. So now let's move on to friction and static particles. When a body is in static equilibrium under the action of a number of forces including friction, you need to consider whether or not the body is on the point of moving. In many cases, the force of friction will be less than mu r, as a smaller force is sufficient to prevent motion and to maintain static equilibrium. In this situation, the equilibrium is not limiting. The reason why the force of friction will be less than mu r is basically, if you remember, the limiting value of friction, or F max, is going to be equals to mu r, where mu is the coefficient of friction, which is a constant, and r is the normal reaction force. The maximum value of the frictional force F max is equals to mu r is reached when the body you are considering is on the point of moving. The body is then said to be in limiting equilibrium. In general, the force of friction F is such that F is less than or equals to mu r, and the direction of the frictional force is opposite to the direction in which the body would move if the frictional force were absent. So basically, if we have a slope like this, and if we have a mass here, if the particle starts moving in this direction, then the friction will be acting opposite to it. And if the particle is on the point of moving in this direction, then the frictional force will be acting opposite, which is towards the left. So let's do some example questions from exercise 7C from the M1 book again, for number 9, which says that a box of mass 3 kg lies on a rough plane inclined at 40 degrees to the horizontal. The box is held in equilibrium by means of a horizontal force x newtons. The line of action of the force is in the same vertical plane as the line of the greatest slope of the inclined plane. The coefficient of friction between the box and the plane is 0.3, and the box is in limiting equilibrium and is about to move up the plane. So therefore we can say that the friction is going to act downwards. So first of all we have to find x. So first let's draw the diagram. Here we have x newtons at an angle of 40 degrees, because this should be 40 as well, because this and this are alternating angles or alternate angles. So this is x. Vertically downwards we have mg, which is 3g in this case, which is at an angle of 40 degrees with respect to the vertical. Then we have the normal reaction force, which is r, and we also have friction, which is acting in this direction down the plane, because the particle is starting to move up the plane, as I've discussed before. So resolving vertically with respect to the plane, we can say that there is normal reaction force acting, and vertically downwards we have 3g, whose vertical component with respect to the slope is going to be 3g cos theta, or 40 in this case, because this is the angle 40. And we also have x at an angle of 40 degrees with the plane. So therefore if this is the plane, this is x newtons. which is 40 degrees. So therefore the vertical component should be x sine 40, which is acting downwards. So therefore we can say that r is going to be equals to this and this, because r is upwards and these two components of forces are downwards. So r is going to be equals to x sine 40 plus 3g cos 40. And this is our expression for the normal reaction force. Now we can say that F max is equals to mu r, where the coefficient of friction is 0.3. So 0.3 into x sine 40 plus 3g cos 40. Similarly, we can resolve horizontally with respect to the plane and say that here we have x cos 40, because this is x at an angle of 40. So this should be x sine and this should be x cos, just like I have mentioned before. And we also have a frictional force which is acting in this direction, which is F max. And similarly, due to the weight, we also have a component in this direction, which is going to be 3g sine theta or sine 40. So therefore, if we look at all of the forces in this direction, we have 3g sine 40 and F max. So we can say that therefore resolving parallelly to the plane, F max plus 3g sine 40 is going to be equals to the upward force parallel to the plane, which is x cos 40. So using our expression for F max, we can say that 0.3 x sine 40 plus 3g cos 40 plus 3g sine 40 is going to be equals to x cos 40. So multiplying the terms, we get 0.3 x sine 40 plus 0.9 g cos 40 plus 3g sine 40 is equals to x cos 40. So therefore x cos 40 minus 0.3 x sine 40 is going to be equals to 0.9 g cos 40 plus 3g sine 40. Taking a common factor of x, we get x is equals to 0.9 g cos 40 plus 3g sine 40 whole divided by cos 40 minus 0.3 sine 40, which is approximately equals to 44.8 Newton. For number B, we have to find out the value of the normal reaction force. So therefore R is equals to 44.8 sine 40 plus 3g cos 40, which is approximately equals to 51.3 Newton. For number 11, we have a box of mass 0.5 kg being placed on a plane which is inclined at an angle of 40 degrees the horizontal. The coefficient of friction between the box and the plane is 1 by 5. The box is kept in equilibrium by a light string which lies in a vertical plane containing a line of greatest slope of the plane. The string makes an angle of 20 degrees with the plane as shown in a diagram. The box is in limiting equilibrium and may be modeled as a particle. The tension in the string is T newtons. So we have to find the range of the possible values of T. So in order to solve this question, we have to understand that the particle can either be moving up the plane or it can also move down the plane. So when it moves up the plane, we have to understand that the frictional force is going to be acting downwards, and if it's moving down the plane, then frictional force is going to try to move upwards. So we have to consider both of the cases separately and then find the values of t. So let's assume that it's going up the plane. So in that case, if this is the normal reaction force, which is R, this is going to be T at an angle of 20 degrees. And then we have mg here, which is 0.5 g, which is at an angle of 40 degrees, as we have learned before. And we also have frictional force acting here or in this direction, depending on how it moves. So let's find out an expression for the normal reaction force by resolving vertically. So if we resolve vertically with respect to the plane, we have R here, and this is going to be 0.5 g cos theta, because this is 0.5 g and this is theta, so this one should be cos theta. And towards the right, we also have T here with an angle of 20 degrees, so this should be T sine 20. So resolving vertically, we can say that R plus T sine 20 is going to be equal to 0.5 g cos theta. Therefore, R is going to be equal to 0.5 g cos 40, as theta is 40, minus T sine 20. And this is the expression for the normal reaction force. And so therefore we can say the limiting value of friction is going to be mu R, which is 1/5 of the expression that we have just found out, 0.5 g cos 40 minus T sine 20. So resolving horizontally and using this form, we can say that F max plus 0.5 g sine 40, which is the theta's value, is going to be equals to T cos 20. So therefore F max is 1/5 of 0.5 g cos 40 minus T sine 20 plus 0.5 g sine 40 is equals to T cos 20. Multiplying, we get 0.5 divided by 5, which is 0.1 g cos 40 minus T by 5 sine 20, and then plus 0.5 g sine 40 is equals to T cos 20. So therefore, rearranging the T terms, we get T cos 20 plus T by 5 sine 20 is equals to 0.1 g cos 40 plus 0.5 g sine 40. So therefore T is going to be equals to 0.1 g cos 40 plus 0.5 g sine 40 and whole divided by cos 20 plus 1/5 of sine 20, which is approximately equals to 3.87 newtons. And for the final case, when the object is about to move down the plane, we can say that frictional force, or F max, is going to act to the opposite direction, which is upwards, and as usual T cos 20 will be here, and similarly here we have 0.5 g sine 40. So resolving horizontally with respect to the plane again, you can say that f max plus t cos 20 is going to be equals to 5g sine 40. So therefore f max is equals to 1/5 of 0.5 g cos 40 minus t sine 20 plus t cos 20 is equals to 0.5 g sine 40. So therefore we'll also get 0.1 g cos 40 minus t by 5 sine 20 plus t cos 20 is equals to 0.5 g sine 40. So therefore, taking the t as the common factor, we can say that t is going to be equals to 0.5 g sine 40 minus 0.1 g cos 40 and whole divided by minus 1/5 of sine 20 plus cos 20, which should be approximately equals to 2.75 newtons. So therefore the range of t is going to be 2.75 is less than or equals to the tension, or the value of t here is less than or equals to 3.87, because this is the maximum value and this is the minimum value of t that can be possible. For the last question, which is from Jan 21, question number 3, we have a parcel of mass 20 kg being at rest on a rough horizontal floor. The coefficient of friction between the parcel and the floor is 0.3. Two forces both acting in the same vertical plane of magnitudes 200 newtons and t newtons are applied to the parcel. The line of action of the 200 Newton force makes an angle of 15 degrees with the horizontal, and the line of action of t Newton force makes an angle of 25 degrees with the horizontal as shown in figure 1. The parcel is modeled as a particle P. So we have to find the smallest value of t for which P remains in equilibrium. So in order to do this math, we have to understand the two possible ways that the scenario can be. Either the parcel is about to move towards the right, meaning that frictional force is going to act towards the left, meaning that the horizontal component of t, which is the t cos 25, has to be greater because it is balancing f max. Since we're told to find out the smallest value of t, that means we have to consider the case where t is minimum. So therefore we have to consider the case when the particle is moving towards the left, meaning that f max and t cos 25 will be in the same direction. So first of all, let's draw the particle again. We have normal reaction force here. We have mg here, which is 20g. We also have t newtons here with an angle of 25. And we also have 200 newtons here with an angle of 15. Meaning that the vertical component of t should be t sine 25. Similarly, this should be 200 sine 15. And the horizontal components should be t cos 25 and 200 cos 15 respectively. And not to mention, we also have f max acting towards the right. To make sure that f max and the t values are aligned in the same direction, to make sure that the value of t is the minimum. So to resolve vertically upwards, we have r plus t sine 25, which is this one, this and this. So plus 200 sine 15 is going to be equals to the weight, which is 20g, Therefore, normal reaction force is going to be equals to 20g minus t sine 25 minus 200g sine 15. Now we can say that the maximum value of friction F max is going to be mu r, and in this case it's going to be 0.3 into r, which is 20g minus t sine 25 minus 200g sine 15. So we can break it down and find 6g minus 0.3 t sine 25 minus 60g sine 15. So we can say that horizontally we have the following forces. We have F max acting. Similarly, we also have t cos 25, and towards the left we have 200 cos 15. So therefore we can say that 200 cos 15 is going to be equals to F max plus t cos 25. Therefore, substituting the value for F max, we have 6g minus 0.3 t sine 25 minus 60g sine 15 plus t cos 25. So therefore, taking a common factor of t, we get in this side minus 0.3 sine 25 plus cos 25 is going to be equals to 200 cos 15 subtracted with 6g, which is this one, plus 60g sine 15, as the signs change when you move the terms to the other side. So therefore the value of t is going to be 200 cos 15 minus 6g plus 60g sine 15 divided by 0.3 sine 25, and don't forget the minus sign, plus cos 25, which is roughly going to be 192 newtons. And this is our answer. Thank you all for watching. Make sure to leave a like, comment, share and subscribe if you enjoyed the content, and see you guys in the next video. Goodbye.